Well, good afternoon, everyone, again. We altered the lectures around due to my colleague running late from his flight. So I'm going to talk to you about radio navigation, basic radio navigation. So next 30 minutes or so, we're going to look at basic radio navigation. And we're going to be looking at the following areas. The non-directional beacon, or NDB, that's the ground equipment. The airborne equipment allied to that is the automatic direction finder, or ADF. Then we'll have a look at the very high frequency omnidirectional radio range, or the VOR. And allied to that, we can have the distance measuring equipment, or DME. And then we're just going to touch on the applications of global positioning system, or GPS. Again, at the end of the presentation, I'll be happy to answer any questions that you have. So let's start with the NDB, non-directional beacon, and the ADF. Non-directional beacons, or NDB, are ground-based transmitters which transmit radio energy equally in all directions. Hence their name, non-directional. We don't get a positive direction from them. The airborne system, or the airborne side of the NDB, is the ADF, or automatic direction finding, or finder. And this will always point to the NDB, the needle, the head of the needle, the arrow pointy bit, will always point towards your beacon that you have tuned. So looking at in a little bit more depth at the non-directional beacon then, we know that it transmits radio signals omnidirectionally. And they transmit them in a wave pattern, just like any other radio transmission, in a waved pattern. The frequency bands that they occupy are the low and middle frequency bands. And the International Civil Aviation Organization allows for these transmitters in the 190 to 1750 kilohertz band. In Europe, generally they transmit on the 255 kilohertz to 405 kilohertz band. The airborne portion, the automatic direction finder, is the automatic airborne unit. And this is used to navigate from one NDB to the next. We can also use it to determine our bearing to and from the NDB, and so therefore plot a line of position on our chart from the NDB that you're tuned to. The indicator and the receiver, of course, are on the flight deck, on the cockpit, with the transmitter being on the ground. The receiver consists of the panel where you dial in the frequencies that you require, and you can also dial in a standby frequency as well. Attached to the receiver, or part of the receiver, which you can't see, and which is part of the aerial equipment on the fuselage of the aircraft, we have two aerials. We have a loop aerial and we have a sense aerial. And between them, they're used to give us our direction, or make the indicator point towards the beacon. Typical control panels are shown on the screen, and they can either be analog or digital. And what we find generally on commercial aircraft is the one on the right-hand side. They have the typical markings of off, which is fairly obvious, the machine is off. ADF, that means you're in automatic direction finding mode, which means the needle will point to the beacon. Or we can then put it into antenna mode, which allows us to hear the ident that the beacon is given. Every beacon that we use for navigation has a Morse code ident, and before we use it for navigation, we need to make sure that the beacon's identification is correct for the one we're using. So each beacon will have a 3-letter code, and therefore that code is then translated into Morse code so we can hear it. So we know that we're tuned into the right beacon. Because also, around the country, many beacons have the same frequency. So you need to be sure which beacon you're actually tuned into. So the antenna portion allows us the option to listen more clearly to the Morse code. The BFO, or beat frequency oscillator position, are for listening to older NDBs. Long-range NDBs, which means all their transmitting power is used for range, and the way they put the ident, because we can't hear the signal because it's too high a frequency band, they key the signal and to make up the Morse code ident. So what the beat frequency oscillator position does is superimposes an audible tone onto that and replicates the Morse code ident. So they're the 4 positions that you will see typically on the control panel. The other one is test. By pressing the test button, that will make the needle go from its current position to normally the 3 o'clock position on the gauge. As soon as you release the test switch, it will go back, hopefully, to where it was indicating before. The bearing indicators themselves can be 3 types. We can have a fixed card, or RBI, which stands for relative bearing indicator. That means its card in the middle is fixed with reference to the aircraft. So imagine you can see the aircraft is in the middle, and the nose of the aircraft will be at 0, and the tail of the aircraft will be pointed to 180. So wherever the needle points to is a relative bearing from the aircraft nose to the beacon. That is not our track to the beacon. It's just where the beacon is relative to ourselves. The next one is a manually rotatable card, normally called the poor man's RMI, because you can rotate the card inside to your current heading. And as we will see later on, current heading plus relative bearing will give us, our relative bearing will give us our bearing actually to or from the station. And that will give us a line of position. The reason it's called a poor man's RMI is because it's a cheaper option than the actual RMI, which the compass card is slaved with the heading indicator. And so for every time you change heading, therefore the compass card changes to match that heading, and instantly from the needles you can see whether you have a bearing, you can see the bearing to and from the station. The bearing to the station is called the QDM, which is a magnetic bearing, and the bearing from the station is called the QDR. So, as we've said then, relative bearings are referenced to the longitudinal axis of the aircraft, that being the longitudinal axis, and we can then use that with our heading to get a line of position or a bearing. So, taking the relative bearing indicator then, relative bearings are described clockwise from the aircraft nose, and you can see the examples on the screen of the relative bearings. So for example here we have relative bearing of 210. That's 210 degrees from the nose of the aircraft. Or we could say that it's plus 30 degrees from the tail. 180 plus the 30 gives us 210, of course. And likewise. So I'll just give you 30 seconds to get your head around those. So, as you can probably gather then, that we could have the same relative bearing at any position around the beacon. So we still don't know what our track to, our bearing to, or from the station really is. So, as I said, we use relative bearing plus magnetic heading, which gives us QDM, which gives us our magnetic bearing to the station, to discover what our bearing is indeed to the station, to sort out the anomaly. We have to do some mental addition. If we take our magnetic heading and we add our relative bearing to that, and it exceeds 360 degrees, then we have to minus 360 off of that to be able to get our bearing. So one example here, magnetic heading 120 degrees. That comes from the compass, and our relative bearing of 150. Therefore, the head of the needle then points to a QDM of 270. Our bearing to the station, if we're taking the borders north, south, west and east, we can now see that we're on a bearing of west to the station. So if we fly west, if we fly until the needle is at the top of the instrument or the nose of the aircraft, we will fly west. Here we have the situation where we have the magnetic heading of 270, or we're going on a magnetic heading of west, and the relative bearing of 120. The two added together work out at 390 degrees, so therefore we minus 360. So that gives us then a bearing of 030 to the station, or by subtracting 180 from it, we've got a bearing of 210 from the station. The easiest way to convert the bearings in terms of 180, you can add 200 degrees to your current bearing and minus 20. That would be the easiest way mentally to do it. Or you can minus 200 and add 20, instead of trying to figure out 180 in your head while you're flying along. We've also established then that QDR is the reciprocal, or the bearing 180 degrees removed from the QDM. And as I've just been explaining, QDM plus or minus 180 will give us our bearing from the station, or our QDR. So with a relative bearing indicator then, some mental gymnastics need to be done in order to determine what your bearing to the station or from the station is. The other trick that we use is by mentally imposing the RBR needle onto the direction indicator, as you see. So instantly then, we can see that our QDM is 030 if we're on a heading of west, just by placing mentally the needle over the direction indicator. And the tail of the needle then, our QDR of 210. So if you're ever stuck, that's the way to do it. Do a mental swap of the needles. So if the QDM is high, in this instance 310, minus the 200 and add 20, that will give you your 180, etc. And there we can see then aircraft heading and relative bearing. The bearing is always the total sum of the heading and the relative bearing. So no matter where you're pointing in terms of heading, given a relative bearing, you could still be on the same line of position in those situations. The rotatable card indicator, or the poor man's RMI, to easily get your bearings, you just simply rotate the card to your current heading. And instantly now the needle will show either your QDM or your QDR. So a very good indicator to use, providing you reset the heading all the time. If you forget to reset the heading, it's going to obviously not give you the line of position that you require. So that's the point. Every new heading, once you change heading, manually rotate the card. The very modern development then is the radiomagnetic indicator, or RMI. And that gives you a continuous readout of your QDM and QDR. The card rotating with the direction indicator. You can use this indicator to point at NDBs. You can also use it to point at VORs, which we'll discuss in a short while, by just using the switches at the bottom here. Normally has 2 needles, so you can tune 2 beacons at the same time, whether you want to choose to tune 2 NDBs or tune 2 VORs, or one or the other, depending on where you are and what's around you. So a very easy instrument to use. To track to and from an NDB, you've got to take into account the wind velocity. If there isn't any wind velocity, so if the wind is calm, then your heading and your track will be the same, and therefore the needle will point to the top of the instrument and you'll be going to or from the station. But it does, again, require some mental gymnastics in terms of visualize your position, what you have to do to intercept a track to or from a station, and then you must track to or from that station given the wind velocity. The difference between track and heading is drift, which is obviously given by the wind. So NDB tracking, no crosswind, heading equals track. Tracking with a crosswind, you need to first establish what the drift is. So flying heading and track first off, just for a minute or so, just to see what the wind's doing to you, and then you can apply the correction into wind. Once you've established the correction then, your heading of your aircraft will be set, and your RMI needle, or your NDB needle, will, from the top of the instrument, show the amount of drift you're experiencing to keep on track. So your heading will differ from your track due to the wind, due to the drift. Next we're going to have a look at is the VOR, or Doppler VOR. And VORs give us continual lines of position, or radials, tracks. And this is obviously an advancement on the NDB. So this actually manufactures lines of position called radials in degrees magnetic. And the station is continually monitored for any malfunction or failure. If the system, if it's detected that the radials are more than 1 degree in error, then the station will be shut down, or the ident of the station will be taken away, so you cannot hear it. So therefore, if you can't identify it, you can't use it. The airborne equipment side of things, we have aerials on the fuselage, we have a receiver and an indicator in the cockpit. Again, with the receiver, you can tune two frequencies, one that is active and one that is in standby for your next beacon. The receiver panel has various functions on it. The flip-flop button there will flip the active and standby frequencies. Off, again, the machine is off. Voice, some VORs broadcast voice over the airwaves. That could be a weather broadcast, an ATIS, etc. So if you want to listen to that, you can just put it into voice to get a clearer reception on the voice. To identify the station, you would put the switch round to ident and pull it out in order to listen to the identification of the station. There are other various selections. You can use two, which are bearings to or from, so QDMs or QDRs, to get a display of them in the window there. The indicators that we use, these are the common ones: the CDI, or course deviation indicator, the RMI, as we've just described, and the horizontal situation indicator, the HSI. That is a VOR and DI all in one. The course deviation indicator, or VOR indicator, is used to select the course that you want. And the needle in the centre will give you deviation from that course you've selected. And the flags will also tell you whether you're going to or from the station. And we'll see just how much that needle will deflect in terms of degrees in a bit. It also shows an off flag as well, if it's unserviceable. So if you have a frequency that's tuned that's not operative, then the off flag will be there, so you know that something is wrong. So by rotating the OBS, we can select under the index here what radial that we want to or from the station, and correspondingly you will get the to or from indication. So the course deviation indicator indicates the aircraft's horizontal displacement relative to the selected course, so where you are in relation to what you've selected, and is totally independent of the aircraft's heading. And this is what confuses most people. When aircraft heading changes, course deviation will not change. So the course deviation indicator then has the markings for how far you are off course. And that's in number of degrees. And each marking is 2 degrees. So when you get to the 5th marking, 10 degrees, and the needle is right out to the side there, you could be 10 degrees or more off your selected track or radial. So it just doesn't mean you're just 10 degrees, it's 10 degrees or more. As we've said, the course deviation indicator is totally independent of the aircraft's heading. With the needle centred, we are on the course that we desired underneath the index, the yellow arrow. So, however you position the aircraft in terms of heading, as long as you are on this radial, the aircraft could be heading in any direction. And because radials are lines of position manufactured from the station, then if you're on that line of position, you will have the from flag indicating to show you that you are from it. When the from flag is shown, as we said, that corresponds to, and the needle centred, that means you are on your radial, the QDR. If we subsequently set the course deviation indicator to 270, then the needle will still be centred because you're effectively on an extension of the 270 radial. But the 2 flag will show, so that means you're going to the station, to that radial. But again, independent of the aircraft's heading, as you can see on the right-hand side, the aircraft's heading 045, something like that, and we've got the 2 flag with the 270 radial displayed. So, as we said, the course deviation indicator then angular displacement from your selected course. As you fly towards a VOR, because the radials are like spokes of a wheel, they get closer together. Therefore, the CDI becomes more sensitive. The course deviation indicator becomes more sensitive. So very small changes in heading are required to turn onto your selected course. The further away you fly from the VOR, the more the radials spread out. Therefore, you can take bigger heading changes for the same. So this is an expanded scale. Angles aren't to scale. Just gives you some idea of the course deviation indicator. So how do we orientate ourselves then to the beacon? Where are we? Well, what we can do is alter the course deviation indicator to roughly our heading and see what indications we get. We know it's independent of the aircraft's heading, but if we select under the index a course that's roughly equated to our heading, then we'll either get a to or from flag, and hopefully we'll see the deviation, that we're not too far away from it. But it will be a command instrument, and it will then give you a command, in this instance, to turn left back onto the inbound course which we've set of 060. So we can follow the needle. We have a 2 flag, it becomes a command instrument. In the second diagram, we've selected 060 inbound, and again we've got the 2 flag, but our heading is more or less 180 degrees removed from that. But the course deviation indicator hasn't moved. You could follow that and not get onto your 060 inbound. So it's telling us lies in the fact that it says the course is to the left of us, when in fact the course is to the right of us. So that's excuse me, that's something to watch out for when trying to intercept a course. So that's the VOR. Next is the DME, which can be allied to the VOR. They can be what we call co-located. So with the DME, that will give you, it will give you an arc or a range or a line of position, how far you are away from the beacon. Couple that with a radial, which will cross it at 90 degrees, and you've got yourself a fix. And you can plot that fix then onto a chart. So the DME then provides an accurate and continuous indication of the aircraft's slant range from the beacon. And as I said, these can be located with a VOR, and therefore we can get 2 lines of position, one of distance and one of radial, and therefore they will cross at 90 degrees and we'll have a fix. So it's very useful for en route navigation and flying in terminal areas, when you're navigating through terminal areas. The principle of operation then is that the aircraft contains an interrogator which will send out pulses of radio energy which will be picked up by a ground transponder. And what will happen is that the aircraft will send out these pulses of energy in pairs at a random frequency. That's picked up by the ground unit or the transponder, which then, after a short delay, will fire those pulses back at the aircraft in the same at the same random rate as they came in, but at a different frequency. So the receiver part of the interrogator then is expecting its pulse pattern, if you like, taken back to the aircraft, but with its frequency changed. So it knows the speed at which it's fired those pulses at, and at what time it started firing those pulses, and the time delay from when it receives those replies to those for those pulses. Speed and time give distance, but the machine has to halve that distance because the time taken is from aircraft to ground and ground back to aircraft. So it will halve that distance to give you the correct DME distance. The indication on the flight deck or in the cockpit is one of distance, of course. But also it can give you an accurate readout of ground speed and time to the station. If you have two systems on board, two DMEs, then you can select either one, number 1 or number 2. You can hold the current DME station that you're tuned into as well. So that's the indications that we get. So there we have it, VOR DME position fixing. The first line of position is the radial from the station, and the DME then is an arc, a line of distance. Therefore, as you can see, both intersect at 90 degrees, and that's the best fix you will get when two lines of position cross at 90 degrees. So you know exactly where you are in terms of distance and bearing. A brief look at GPS for giving us a position fix. GPS then, Global Positioning Satellite System, and that's the common one that we use. In order to fix the aircraft's position, we need ranges from satellites to give us that cross-cut that we're after. So one satellite gives us one line of position. Two satellites give us a fix of where we are on that first line. And then a third is used in order to confirm that position. So at least 3 satellites need to be in view in order for you to get a position fix. A 4th satellite would be used to determine your height above the ground, or your altitude above the ground. GPS applications then. Currently in this country, we only use them for non-precision approaches. We have a GPS approach here at Shoreham, which we use, but it's non-precision, which means it has high landing minimas and visibilities, but a lot more accurate than an NDB approach, which we also have here. GPS are used for routings in the terminal area, so navigating in terminal areas, and for en route navigation. But GPS is very much still a secondary form of navigation, not a primary. So therefore, pilots will always have to use the old-fashioned VORs, DMEs, NDBs and such, until the accuracy of the GPS is such that it can be trusted. So there we have it, just a brief look at the basic radio navigation systems and their principles, and I'm happy to take any questions.